Hello, Math 120, and this is Professor Gonzalez, and I'd like to do some problems from homework section 10.4, which is taking a look at the binomial theorem. So what we're doing here is expand the binomials, or expand, number one says expand the binomial using the binomial theorem. So I think I want to do a little background about binomials and just kind of give some context to this whole thing, and then maybe give a little background on how the theorem kind of comes together so you can remember it without having to just memorize a formula, I guess. So let's see. Let's first start out. And what is a binomial? Well, a binomial would be the addition of two monomials, something like that, right? So if we take a look at that binomial and we raise it to the 0 power, we get 1, so that's not very exciting. And if we take x plus y and raise it to the first power, that's just 1x plus 1y. Okay, well, it gets a little more exciting when we raise it. We take x plus y and raise it to the second power. Now we know that is just x plus y times x plus y. Whoops, getting a little sloppy there. And when we multiply that out, I guess we'll go ahead and do the old, as you guys like to call it, foiling out. Well, that's just going to be what? X times x. That's going to give us x squared. And x times y, that's xy. And y times x is xy. And y times y is y squared. And when we combine the like terms here, right, we get x squared plus 2xy plus y squared. Okay, so we're going to start seeing a pattern emerge here that I want to highlight. The first thing I think I want to show is that we have these coefficients that are showing up. So I want to start highlighting these coefficients. Whoops, on this one, 1, 2, 1. Let's get rid of that little one. Whoops, got rid of a little too much there. Okay, so there we have. So now, what we have is, let me start again. What we have are binomials, and these binomials so far we have it raised to the 0 power, first power, second power, and we're expanding them. So when we're multiplying it out, we're expanding them. So the next one we'd want to look at is something like, what about x plus y? Let's raise that to the third power, which is x plus y times x plus y times x plus y. Now we already know what x plus y times x plus y is because that's the previous one we just did, right? So that's just going to be x squared plus 2xy plus y squared. Now that still needs to be multiplied times x plus y. And so you can see expanding these binomials, we're only to the third power. It really gets pretty labor intensive. As you notice, if we multiply this out, right, we're going to have x times, whoops, that didn't work. We're going to have x times x squared, which is x cubed. We're going to have x times 2x, which is plus 2x squared y. And then we have x times y squared, which is plus xy squared. And then, of course, we continue with the distribution y times x squared, which is x squared y, and y times 2xy, which is 2xy squared, and then y times y squared, which gives us y to the third power. Okay, so now, combine like terms. Well, we've got x cubed. Let's see, so let's combine. Where do you see x squared y's? I see two of them there. X squared y's and one right there. So that's going to give us plus 3x squared y. And then moving right along here, how about x y squares? X, and then we got 2xy squares. So that, of course, makes plus 3xy squared. And then finally, I've got a plus y cubed. And that is the result of expanding x plus y cubed. So let's see. So the pattern that I want to start pulling out here. Of course, I wanted to show the coefficients here. So the coefficient on this one would be 1, 3, 3. Let me fix that a little better so I can squeeze in a 1 right here. So see those coefficients. We've got 1 up there, we've got 1, 1, then we've got 1, 2, 1, and then I've got 1, 3, 3, 1. So the first thing I think that I want to show here is there's something that correlates with that. And let's see how much space I have. There's something that correlates with that. Something called, how far can I go down here? I'm getting lost. Something called Pascal's triangle that I can take a look at. And Pascal's triangle looks like this. And I think I'm going to do it in red just to show that it's these coefficients we're talking about. Pascal's triangle looks something like this. 1, and then the next line of it is 1, 1. And the next line is 1, 2, 1. And the next line is 1, 3, 3, 1. Now you might ask, where the heck are these coming from? And where it's coming from is taking a look at, the sum of the two numbers diagonally above. So 1 plus 2 is 3, right? 2 plus 1 is 3. So you guessed it, I believe. You always start with 1 and end with 1, by the way. So this next one would be 1, and then 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4, and you end with 1. And so then you can see this one is going to be what? 1, 5, 10, 10, 5, 1. So, and let me get rid of some of these little connecting pieces. Also, I think I'm going to write this so we can make sure our eyes focus on the line that we're talking about. So if you go back here, you can see when we had to the 0 power, so that's where we had a 0 power, or 0th power. I don't know if that makes sense. Let's just put 0. So 0, that got us 1. And when we had the first power, so number 1, that get us 1, 1. And you can see when we had second power, what does that line look like? 1, 2, 1. And third power right here, 1, 3, 3, 1. And there it is, 1, 3, 3, 1. And I think maybe a different color so it kind of sticks out a little better. Okay, so we can definitely see a pattern. We can continue to make that triangle larger and larger just to hit higher powers. And that is going to help us do these problems expand. These are the coefficients that come from Pascal's triangle. Now, Pascal's triangle has another connection. Did I leave enough space? Pascal's triangle has another connection, and that is using combinations, which is sort of a grouping principle. And I'm going to show that, but it's not really necessarily something you have to use for this class. But we can find these numbers by using a formula called combination. So this would be a combination of, we're on line 5, choose 0. And then this one would be a combination of 5, choose 1, combination of 5, choose 2, combination of 5, choose 3, combination of 5, choose 4, and that's a combination of 5, choose 5. So, what is this combination formula I'm talking about? Like I said, you can just use Pascal's triangle, and it's very easy to write up and make very fast. But the combination takes a little more, but it's something we use often in combinatorics and probability, in statistics 300. But let me show you the formula for this. The formula for this combination is the combination of n choose r is going to be equal to n factorial over r factorial times n minus r factorial. I'm just going to do this once, and like I said, you could just use Pascal's triangle, or you can use combinations if you'd like. But if I was going to do show my combinations, use the formula on this one, I should get 10. And let me just do it just to prove it to you. So if I was looking for a combination of 5, choose 3, that would actually be 5 factorial up top over 3 factorial using my formula times 5 minus 3 factorial. So simplifying this, I know this is 5 minus 3, which is 2 factorial, okay? So now I have 5 factorial over 3 factorial times 2 factorial. Now, what are factorials? Well, factorials is a technique. It comes in very useful. It's very useful with combinations and permutations and finding probability. But let me just show you. 5 factorial doesn't mean 5. It means 5 times 4 times 3 times 2 times 1. It's just the product of descending numbers down to 1. And so 3 factorial, let me say it again, 3, this one right here, 3 factorial would just be 3 times 2 times 1, and 2 factorial would just be 2 times 1. Now, the fact that these are factors, we are allowed to reduce common factors. So common 3s are factors, common 2s are factors. Of course, 1s are already reduced completely. And of course, you can reduce the 2 and the 4 also. But you could also just say up top, 5 times 4 is 20, and 2 times 1 is 2, and 20 divided by 2 is 10. And wow, look at that. We got 10 using the formula for combinations, which is the same as using Pascal's triangle. Now, Pascal's triangle is just really useful because, just by ripping out this formula, or the triangle very quickly, you can get, all the coefficients, 1, 5, 10, 10, 5, 1, quickly for expanding a fifth degree binomial. So let's put this into practice. And before I get going, I want to show one more thing here to try to really show you the pattern. Okay, so one more thing here. Let me get a little more space to work. So when we're looking at this first particular problem, let's see, do I want to use color? I think I am going to use color. So what I'm going to do is I'm going to use red for the coefficients. So first of all, in this first one, you can see the coefficients that we have are going to be 1 and 1. People yelling at dogs out there. I don't know if you can hear the drama in my house right now. But anyhow, so the way this goes, concentrate. The way this goes is you take, the way this goes is you see that this is the first power, right? So you go to Pascal's triangle and you look at the first, and it has a 1 and 1. So look at that. 1 and 1 is written down. Now the rest of the pattern is not really easy to see here, but I'm gonna make it pop out here. You take the first variable. I'm going to write it both places, and it's raised to the power that we have, so first power, and you just descend the power. It's going to make more sense with bigger expansions, but this is 1 and then 0. Now the other variable, the second variable, is a y, and that is being multiplied, and of course we have addition here, but that ascends, so it starts at 0 and goes up. Now it goes up to the power that you started with, right? Notice this is first power, and so it's going to go from the blue is going to go 1 to 0, and the green is going to go 0 up to 1. Now we know that when we have a base, it's raised to the 0 power. That's just 1, right? That happens here too. This is raised to the 0 power, so that's just 1. So ultimately, when you simplify it, you just get this. Okay, but I'm trying to do this for pattern purposes. So let's take a look at the next one. If I use the same color scheme here, that's x. Okay, so let's go ahead and see how this should expand out. Well, first of all, I see it's a second power. So I go to my second degree and I look at the coefficients, which happen to be 1, 2, 1. Okay, so I'm going to write 1, 2, 1. Those are the coefficients. Now, all I have to do is take a look at my first variable, which is the blue x. I'm going to write that. And this is going to start with the power that I'm starting with, second degree. So it's going to start with 2 and descend 2, 1, 0. And then I'm going to take my second variable, y, and I'm going to write that, and I'm going to ascend it. Ascending order, so it's going to be 0, 1, 2. Okay, now simplify. And once again, I know that that y to the 0 is just going to be 1. And I know this blue x to the 0 is just going to be 1. And so then we simplify it, right? We end up getting this. Just the same thing we did when we manually sort of distributed it out, right? So we end up getting the same thing. And so this becomes, it's not as valuable, you know, when you're just having the second degree binomial, but third degree, a little more valuable, fourth, fifth, sixth, oh my goodness, it's a lifesaver. So you can see the amount of work that was done on this third degree right here. And by the way, we sort of just cheated and just wrote that down from the work we did in the previous one. So you would have had to have done this work on top of that work. But anyhow, how would I do it using this pattern, which is actually called the binomial theorem? Well, if I was going to do this problem right here that said, let's see, it said x plus y to the third power, here's how I would do it. Say, okay, the power is 3, so I go to my Pascal triangle that has 3 on it, and the coefficients are going to be 1, 3, 3, 1. So I write those out. 1, 3, 3, 1. And then, just like I did before, I see the x goes here, and that starts with a power of 3 and drops down to 2, 1, 0. And then I go with my y value. That goes here, and this is, of course, being multiplied. And this starts at 0 and goes up 1, 2, 3. Now, one way to kind of double check yourself is to realize that this power is 3, and when you add up the exponents, it better equal 3, right? 3 plus 0 is 3, 3 plus 1 is 3, 1 plus 2 is 3, 0 plus 3 is 3. And so that has to be true. Now, you just go through and simplify it. That's a 1, and that to the 0 power is 1. And then when you simplify this down, well, I've got 1 times 1 times x to the third, so that's just x to the third. And I've got a 3, x squared y to the first. And this next one, I've got a 3x to the first y squared. And I've got 1 times y to the third. And you can see I end up getting the same answer I got back here. When I did all that expanding, I got it in a really quick way. And much more accurate, because you could easily lose some term over here when you're trying to do this. Now that was just 3. We're going to do 4 and 5th powers, and it's just going to be really much easier if we use Pascal's triangle or combinations, but we'll use Pascal's triangle on this. Okay, let's go ahead and start this fun now. Expand the binomial using the binomial theorem. So we see a 4th degree. So we go down here to my little notes here, my Pascal's triangle. 4th degree is here. What are the coefficients? 1, 4, 6, 4, 1. 1, 4, 6, 4, 1. 1, 4, 6, 4, 1. And now I take my blue x and write it in: x to the 4th, x to the 3rd, x to the 2nd, x to the 1st, and of course x to the 0. Then I take my next 10. Well, this is going to be times 10, 10 to the 0, 10 to the 1st, 10 to the 2nd, 10 to the 3rd, and 10 to the 4th. Now, expanding this out, of course, we know that this is just going to be 1, and we know that this x to the 0 is going to be 1. Okay. So this first term is 1 times x to the fourth. This is just x to the fourth. I think let me write this down just a little bit further. This is just x to the fourth is what this becomes. Now this next one, I've got, right, that's 4 and that's 10. So 4 times 10 is 40, and then I've got my x to the third. Okay, next particular problem, I've got 10 to the second, which is 100. And so I've got 6 times 100, that's going to give me 600. And then don't forget your x to the second power. Okay, and then keep it going. I've got, let's see, this 10 to the third is 1 with 3 zeros, so that's 1,000. And I can see that I've got this 4 times 1,000, which is going to be 4,000. And don't forget your x to the first. And then finally down here, I've got 1 in red, 1 times 1. But this guy right here is 10 to the fourth, which is 1 with 4 zeros, which ends up giving me 10,000. And that is the expansion of x plus 10 raised to the fourth power. So we get x to the fourth plus 40x to the third plus 600x to the second plus 4,000x plus 10,000. And you would have gotten that, but you had to have done a lot of multiplication, extended multiplication, and then collecting like terms would be a real pain. Oh, now here we go to the fifth power. Now how are we going to do this? Well, we're going to go down to Pascal's triangle again. We're going to look at the fifth line. It's really 0 is the first one, so got to be careful on how you count this, but it's the fifth power, and those coefficients are 1, 5, 10, 10, 5, 1. Okay, I got to be careful trying to squeeze all that in, and it is, let's go over here, 1, 5, 10, 10, 5, 1. Hopefully I have enough space. So now I'm going to put a little plus here just to make sure we separate that, and everything else in there is going to be multiplied. Okay, now continuing with the same pattern. What color did I use first? Blue, right? So I have C. So this C value is going to be C to the fifth, C to the fourth, C to the third, C to the second, C to the first, C to the 0. What else do I have? I've got 3. This is going to be 3 to the 0, 3 to the first, 3 to the second, 3 to the third, 3 to the fourth, and 3 to the fifth. Once again, now we see the original power here is fifth power, so each one of these powers must add up to 5. 3 plus 2 is 5, 2 plus 3 is 5, 1 plus 4 is 5, and 0 plus 5 is 5. So that's a good little check to make sure we're good to go there. Of course, this is going to be 0, so I'm just left with C to the fifth power. Now I've got 5 times 3 is 15, C to the fourth power. Now don't forget that 3 squared is 9. So now I've got 10 times 9, which is going to give me 90. And this is C to the third power. And don't forget that 3 to the third is 27. So now I've got 27 times 10, which gives me 270 C to the second. And we're getting there. We have 3 to the fourth power, 3 times 3 times 3 times 3, which is 81. And 81 times 5, well, that's going to give us 405, and that's C to the first. And then finally, of course, C to the 0 makes this a 1, and 3 to the fifth is 243. Of course, that gets multiplied by 1, so that's just 243. And there is the answer. We just expanded a binomial to the 5th power, which would really take a ton of time and would be very easy to miss a term when you're collecting like terms or multiplying and get it wrong. We have c to the 5th plus 15c to the 4th plus 90c to the 3rd plus 270c to the 2nd plus 405c plus 243. Perfect. Let's move on and expand another one. Now we've got a negative here, and we've got to be a little bit careful with the negatives. I'll show you how to do it. Take a look. We're looking at our 4th. So what are our coefficients for 4? It's going to be what? 1, 4, 1, 4, 6, 4, 1. 1, 4, 6, 4, 1. 1, 4, 6, 4, 1. Okay. And space-wise, I may need to move that over just a little bit so I don't run out of space over there. Okay, so now just like we did before, we're going to use x as our first term. So it's going to be x to the 4th, x to the 3rd. Let me zoom in so I can make it fit a little better. X to the 2nd, x to the 1st, and x to the 0. Now next of all, we're going to take, now you have to take the sign. That's the trick. This is negative 4 to the 0, negative 4 to the 1st, negative 4 to the 2nd, negative 4 to the 3rd, negative 4 to the 4th. Remember, each term must add up to the 4th power. Okay, I guess I had enough space. Okay, now what I need to do, of course, I always recognize that this is going to be just a 1. Also recognize that x to the 0 is just going to be a 1. So now I've got 1 times 1, so this first one is just x to the 4th, first term rather. Here's where the negative comes into play. I've got a 4 times negative 4, which is minus 16, x to the 3rd. So that negative caused a negative coefficient of negative 16. However, you'll see when it's raised to a positive power, negative 4 squared is positive 16, and so we get back to a positive term now. So now we've got 6 times 16, and 6 times 16 gives me 96. So we've got plus 96, and we have x to the 2nd. Now we have an odd exponent, so negative 4 to the 3rd power is negative 64, so it's going to cause this term to be negative rather. Negative 64 times 4 is going to be negative 256, and we have x to the 1st. And then finally we have negative 4 to the 4th, which makes it positive. Four negatives become positive 256, and so we have plus 256. We just expanded that binomial raised to the 4th power. So we get x to the 4th minus 16x to the 3rd plus 96x squared minus 256x plus 256. Done. Number 4. Okay, so now we have a variable with a coefficient with it, but it's still the same procedure. The very first thing you want to do is look up those coefficients. And there they are right there for the 4th. It's 1, 4, 6, 4, 1. 1, 4, 6, 4, 1. That was 1, 4, 6, 4, 1. Of course, we separate with plus. We come through and we realize that this first term is a 2p. So we need to use parentheses, 2p to the 4th, 2p to the 3rd, 2p to the 2nd, 2p to the 1st, and 2p to the 0. Now the next term is a positive 1, so yeah, that's not going to do much to it, but we've got a positive 1 to the 0, 1 to the 1st, which is 1, 1 to the 2nd, which is 1, 1 to the 3rd, which is 1, and 1 to the 4th. I'm just doing this really for power purposes. I mean power for pattern purposes to make sure we're seeing this pattern, but I think you can see what's going on. All the greens are going to be 1. This first blue, okay, we've got 2 to the 4th power, right? You can see it right here, 2 to the 4th power, well, that's 16, right? And then you have p to the 4th power, that's p to the 4th. So that is going to just, and it gets multiplied by 1 times 1. So this is just 16 p to the 4th power. Now let's do the next one. This is 2 to the 3rd, which is 8, p to the 3rd, which is just p to the 3rd. Now we need to multiply 4 times 8, p to the 3rd, times 1. So 4 times 8, that's going to give me 32. And I've got p to the 3rd. Okay, this blue is 2 to the 2nd, which is 4, and p to the 2nd, which is p squared. So now we have basically 6 times 4 times 1, or 6 times 4, which is 24. And then I've got p squared. And then, yeah, we're pretty much good because this is 1 to the 3rd, which is 1. So now we just have 4 times 2, which is 8. And that's p. And I've got a 1. And I do know always that this is raised to the 0. So that's 1. And I also know that 1 to the 4th power is 1. So that last term is just 1. So we have a final answer of 16p to the 4th plus 32p to the 3rd, rather, plus 24p to the 2nd plus 8p plus 1. Awesome. And here we are with the last problem here. And we're doing a 5th. So let's see if we can get this. We take a look at the coefficients for the 5th, which is 1, 5, 10, 10, 5, 1. Okay, I got to fit it. That's the hardest thing. 1. So it's 1, 5, 10, 10, 5, 1. Get a little more space there. I think that's good. Okay, so now we have a plus here, plus here, plus here, plus, plus. Let's go through with our green was our first color. No, our blue was our first color. I'm going to zoom in so I can try to squeeze all this in. I've got a 4z. So this is 4z raised to the 5th power. 4z raised to the 4th power. 4z raised to the 3rd power. 4z raised to the 2nd power. 4z raised to the 1st power. And 4z raised to the 0 power. Take a look at our next coefficient, which happens to be, negative 2. Got to be careful. This is negative. I'm going to zoom in a little more. Negative 2 raised to the 0. Negative 2 raised to the 1st. Negative 2 raised to the 2nd. Negative 2 raised to the 3rd. And you know this negative changing powers is just going to alternate the negative sign. Negative 2 raised to the 4th. And finally, negative 2 raised to the 5th. And that guy right there is supposed to be raised to the 0 power. Okay, let's see what we can do here by simplifying a little bit. In blue, right here, I've got 4. So notice, maybe I'll zoom in again. This says, this is basically 4 to the 5th power and z to the 5th power. And then negative 2 to the 0, so that's just going to be 1. So really what we're looking at is what is 4 to the 5th power? Well, that is 1024. So we multiply all that together, we get 1024 z raised to the 5th power. Okay, next piece. I don't want to give it away. Let me get rid of that. Next piece, I think the next piece we're going to have to simplify is, this is 4 to the 4th power. So 4 to the 4th power is 256. Z to the 4th power is z to the 4th. So you can see all the pieces that we need to multiply. 5 times 256 times a negative 2. 5 times 256 times a negative 2. That gives me a negative 2,560. Oops. 60. And there is a z to the fourth power. Next, looks like I have in blue, I've got a 4 to the third power. So that's 4 times 4 times 4, which is 64, and a z to the third power. Now in green, I've got negative 2 to the second power, so negative 2 times negative 2 is 4. So what I need to multiply is 4 times 64 times 10. That's going to give me a positive. Where am I at? Third power for that. So 4 times 64 times 10, that's going to give me positive 2,560, and that's z to the third power. And so all of that simplified to that. Okay. I'm going to stretch this out so it kind of matches up with what I'm working with above. In blue, I've got 4 to the second, which is 16, z to the second, which is z to the second. Now be careful. In green, I've got negative 2 times negative 2 times negative 2, which is negative 8. It's going to cause this whole term to be negative. So on this particular problem, I basically have 10 times 16 times negative 8. Well, that's going to give me, I got to get rid of this. That's going to give me a negative 1,280 z squared. Okay, moving right along here. 4z is to the first power, so that's easy. Negative 2 to the fourth. Okay, so 4 negatives being multiplied, that's just going to be 16. Okay, so now what we need to do is we need to multiply 5 times 4 times 16. That's going to give us a positive 320, and that's z to the first power. And here we are with the last bit of information that we have to simplify. Well, we know that anything to the 0 is going to be 1, and negative 2 to the fifth is negative 32, and that just gets multiplied by 1, so I can see what my final term is, minus 32. Let's zoom out and take a look at all the beauty of this thing. Looks something like that. Let's double check it. It should be 1024 z to the fifth minus 2560 z to the fourth plus 2560 z to the third minus 1280 z squared plus 320z minus 32. And there it is. We just expanded out this nasty fifth degree binomial that had a negative involved, but we did it. Okay, everybody, I hope you are doing great. Finishing strong. This is it. This is the last particular section. Hope everybody's doing great. Finish strong, study hard. Take care. Talk to you soon. Bye.